Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the branch sums. This is a pretty straightforward question. You have to write a function that takes in the root node of a binary tree. So if you take the example that I have in front of me here, the root node would be the node with the value 1. And this function has to return a list of all of the branch sums in this binary tree. Now, what is a branch sum? It is the sum of all the values in a particular branch in the binary tree. And what is a branch? A branch is a path in the binary tree that starts at the root node, so at the node with value 1 in the example here, and that ends at one of the leaf nodes. In our example, we've got 5 leaf nodes, 8, 9, 10, 6, and 7. Leaf nodes are the nodes at the very bottom of the tree. So, as you can see, the answer to this problem for the example in front of me is this array here at the top, where we've got 15, 16, 18, 10, 11. All 5 of these numbers are obtained by summing up the numbers in the various branches. So for instance, you take the first branch, this branch here, and if you add up these 4 numbers, they sum up to 15. Similarly, if you add up these 3 numbers here, these 3 numbers add up to 10, and so on and so forth. So pretty straightforward. This problem is also fairly simple to solve. We can do so recursively with little to no trouble. The main idea is that we are going to be calling a recursive function on each node in the tree, starting at the root node, that calculates the branch node, or the branch sums rather, for the tree rooted at that node, but we keep track of a running sum, meaning the sum that we've obtained by calculating values or adding values from nodes above us at every recursive call in this whole algorithm. So for instance, if we start at 1 here, we would call whatever our recursive function is on this root node, and we would say right now our running sum is 0. So I'm actually even going to write in purple next to it, or maybe in green, 0. Right now we haven't added any numbers, so we have 0, and we call our method on this 1. Now our root node has 2 children nodes, right? It has one to the left and one to the right. So we would now call the recursive function on these 2 children nodes, but we would pass in our running sum, which at this point in time would be 0 plus 1, where 1 is the value of the node that we were currently at, the root node, 1. So 0 plus 1 is equal to 1, so we would now call recursively this function on these 2 nodes, and we would have the running sum as 1. So I'm going to write it to the left and to the right of them. At both of these nodes, we would say, okay, we still have children nodes. So like for instance, this 2 here has a 4 and a 5 to the left and to the right. The 3 has a 6 and a 7. So we can keep going down. So we're going to once again recursively call this function. But this time around, we're going to pass the new running sum, which for the 2 here on the side of the 2, it would be 1 plus 2. And on the side of the 3, it would be 1 plus 3. So here we've got obviously 3, and here we've got obviously 4. And so now, I erase this, we now call the function recursively on all 4 of these values here with, we said we had 3 here. So 3, 3, 4, and 4. Once again, the 3 comes from the fact that we've added 2 plus the running sum that we had there, which was 1, which came from the root node. And this 4 comes from the fact that we added 3 plus the running sum, which was 1, which came from the root node. Now at this point, we can keep going. So with the 4, we see that we have 2 children nodes. So we would call the function recursively on both of those, and we would add 4 to the running sum 3 and pass this total as the running sum to these 2 nodes. So that would be 3 plus 4 That's 7, right? So we can pass in 7 here. And here, sorry, we had 3. Here we pass in 7. At the 5 here, we would pass in 3 plus 5. 3 plus 5, which would be 8. And then at the 6 and the 7, we're dealing with leaf nodes. And to be honest, we're dealing with leaf nodes down here as well, with the 8, the 9, and the 10. Now, taking a small step back, or a small tangent, because we're going to do this recursively, we're likely going to call this function in a sort of depth first search way. So we would likely have gone through the entire left side of the tree before we would have even gone to this right side. Here I kind of did them in tandem to show you, but keep in mind, and this will be clearer in the code, that if we do depth first search here, we would start with the left side of the tree. In fact, the order of the branches that we would go through would be first this one, then it would be this one, and it would really be, the way that it would really be it would go down here all the way to the 8, then it would go back up all the way to the 9, then it would go back up here all the way to the 10, then back up to the 6, and then to the 7, right? Because again, we're using depth first search. But okay, now we are at the leaf nodes. What do we do at the leaf nodes? Well, we are at the 8, and we can say, hey, we have neither a left node nor a right node. So we know that we are a leaf node. So in that case, we are going to once again sum up the current value and the running sum. So 8 plus 7, this is going to be 15, and we're going to add that, I'll undo this stuff, and we're going to add that to a list of sums that we might be passing down as well. So I'll probably be passing down, at every recursive call, I'll be passing down a little array of sums that starts out empty, but suddenly once we are here at the 8 and 7, this array of sums, we add 15 to it. Then we go back to the 9 here, and we've got 9 plus 7, which is 16, and there's no left or right child node. So we're going to append 16 to our array here, and now we've got 2 values. Then we go back up here and down here, and we are at the 10 and the 8. So we add both of these, and we have no left node, no right node. So we know we're at the end. We're at a leaf. We've calculated a branch sum. So we append the sum of the running sum, 8, and the value 10, which is 18, to our running list of sums. Then at this point, we go back up. We go down to this side here with the 6. 6 plus 4 is 10. We have no left node and no right node, so we add this to our list. We've got a 10. And then finally, we go here to the 7. 7 plus 4, and we've got 11. And as you can see here, this is our solution array. This is what we wanted to return from the beginning. And we, at this point, we've probably passed down this array right here. We've probably passed it to our recursive function. We'll see what that looks like in the code. But at this point, we have it filled up, and we can return it as part of our main function and be done with the algorithm. So as far as space-time complexity, this algorithm is going to run in O of n time, where n is the total number of nodes in the binary tree. So we're going to write time equals O of n. Why is it O of n? Well, we have to traverse through all of the nodes, all of the n nodes in the binary tree, to account for each of their values when we're calculating the various branch sums. At every single node, all that we're doing are constant time operations. We're adding the value at that node to the running sum. We're maybe checking if the left node exists or if the right node exists at that node. But overall, we're just doing constant time operations n times at each node, right? or n times in total, because we're visiting n nodes. So that's why we have a time complexity of O of n. Now the space complexity is a little bit more complicated. It's more complicated because it's affected by two things. It's affected by the list of branch sums that we have to return, which is surprisingly complicated, and we'll get into that in a second. And it's also affected by the recursive nature of our solution, of our algorithm. The recursive part of our algorithm affects the space complexity in that we will have multiple recursive function calls on the call stack at once. So on average, when we're dealing with a balanced binary tree, a binary tree that sort of looks like this one, right, where you don't have one super long branch, right, you have balanced lengths for the branches. Here, the space complexity implications of the recursive calls is going to be log of n. And the reason it's log of n is because whenever you're making a recursive call, let's say, you start at the root node and you go to the node with the value 2, you're suddenly eliminating half the nodes. Then you go to the value 4 and you're eliminating another half of the nodes. Then you go to the value 8 and you're eliminating another half of the nodes. And similarly, then you go back up, right? You had 4 function calls or recursive calls on the call stack. Then you go back up to the 3 and you go down to the 9 and you've eliminated this half of the nodes at this tree. And so basically you will never have more than that many calls on the call stack, which ends up being log of n because you are eliminating half the nodes in the remaining tree at every recursive call. Now, in the worst case, when you're dealing with a tree that's very skewed, like imagine a tree that goes 1, 2, 3, 4, 5, right, that only has nodes to the left, in that case, you would have O of n space from the recursive calls because you would have 1, 2, 3, 4, you would have n recursive calls at once since you're going all the way down to the leftmost side, which happens to be all of the nodes in this terrible case. Okay, so that's the space complexity implication from the recursive function. This is pretty standard for binary tree algorithms or BST algorithms. However, the complicated part comes from this branch sums here. How many branch sums are we going to have? Because that is going to dictate the length of this list. Okay. The best way to do this without going crazy or trying to do too complicated of math, because at the end of the day, this is a math problem, because here it's basically the number of branch sums, which can be translated into the number of branches in a binary tree, which can be translated into the number of leaf nodes in a binary tree, and that's actually a pretty math-heavy problem. You can actually look up, proofs, full-on math proofs for how many leaf nodes there are in a binary tree of n nodes, and there are actually really cool formulas that you can derive that will allow you to calculate the number of leaf nodes in a binary tree, the number of non-leaf nodes in a binary tree. But the best way to think about it here is that you would never have more than n branch sums because you have n nodes, so it would never make sense for there to be more than n branches or more than n leaf nodes. So already you know that our space complexity is bounded by O of n, but you also know if you look at an example of a balanced binary tree, like I'll rewrite an example so that you can see, because here I've kind of scribbled around this one. Imagine you've got 1, 2, 3, 4, 5, 6, 7, right? You can kind of see that there's roughly half of the nodes at the bottom portion, at the leaf nodes, right? There's roughly half, and if I were to add another level, right, like 8, 9, sorry, what am I doing? 8, let me undo this, 8, 9, 10, 11, 12, 13, 14, 15. You can kind of see again, it's like there's roughly half of the entire nodes in the entire binary binary tree that are leaf nodes. So roughly n divided by 2. And n divided by 2 would be O of n as far as complexity analysis. So our space complexity is going to be O of n. And again, another way to think about it here is in a balanced binary tree, every new level is a new power of 2. Right? You've got 2 to the power of 0 nodes at the top. 2 to the power of 0 is 1. There's a 1 root node. Then you've got 2 to the power of 1 nodes on the second level. 2 to the power of 1 is 2. There are 2 nodes. 2 to the power of 4, 2 to the power of 2 is 4 nodes here. And you keep adding a power of 2 until you have, 2 to the power of, k. But so basically the leaf nodes, whenever you add a new level of leaf nodes, you are multiplying the number of nodes by 2, right? So that, again, can sort of help you derive the fact that ultimately you are going to have roughly half the total number of nodes as leaf nodes, and roughly half of n is going to be O of n space. So again, here I took a bit of time. I realize that this is a lot more complicated than it probably should be for a seemingly simple problem. I would encourage you to probably check out some of the math proofs for how many leaf nodes there are in a binary tree. They can be kind of interesting. It'll probably help you grasp binary trees a little bit better. But this is probably all that you would need in an interview. And to be honest, you wouldn't even have to go through all of this. You could probably, very quickly say it out loud why it's roughly half of the binary tree in terms of leaf nodes, and therefore why you have a space complexity of O of n. And to be honest, here, I'll add on one more thing. I would argue that in an interview, you could even just tell your interviewer, hey, we know that we are going to be bounded by O of n because we're not going to exceed n branch sums. That just would not make sense. And already that should, give the interviewer enough signal for where your head's at. Anyway, with that, let's dive into the code walkthrough to see what this looks like. All right, so we've got our branch sums function defined. It takes in the root of a binary tree. We've got the binary tree class defined for us up here. Every binary tree node has a value, which is just going to be an integer or a number. And it's also got a left and a right node. These are initialized to the none value or the null value, but they can also be set to be binary tree values, right? So that we have a binary tree, as you would expect. And so this branch sums function that we have to write, we said in the conceptual overview that we want to do this recursively. And we said that in our recursive function, or our recursive sort of logic, we are going to be passing in the running sum, or keeping track, rather, of the running sum that we've been calculating. And at every node, the running sum will be equal to the sum of all the nodes above it, basically. So we're going to want to pass a second parameter to this recursive function, and we might actually even want to pass a third parameter because we said we would also be keeping track of a running list of branch sums, and we would be appending values to this running list. So what I'm going to do here is I'm going to define a brand new function, which is going to be our actual recursive function. I'm going to call it calculate branch sums. And this recursive function is going to take in a node, of course. It's going to take in a running sum and a list of sums. And in our main function, we are going to be making a call to the recursive function with our root node. And for the starting running sum, if you remember in the conceptual overview, we said, hey, at the root node, we have no running sum, so let's just initialize it to 0. So I'm going to put 0 here. And then finally, for the sums, we're probably going to want to declare a list. So I'll call it sums. I'll declare it right above. Sums is going to be an empty list. And I suppose we can just return sums right here. And so this calculate branch sums method is going to be our recursive function that has the side effect of appending branch sums to this list here. Doesn't return anything, it just appends values to this input list. There are probably other ways that you could do this. Maybe you could write this function in such a way that it returns values and doesn't have a side effect, but I'm just going to go with this. So, what do we do in the recursive function? Well, the first thing that you might think is we calculate the new running sum. Like we add whatever the value of our node is to the running sum. So we'll do new running sum equals running sum plus node.value. What else do we want to do? If we are at a leaf node, we've effectively calculated the branch sum, right? This value, new running sum, if we're at a leaf node, if our node is a leaf node, then this new running sum is a branch sum. So we're going to say, if we're at a leaf node, let's add this new running sum to our sums list. So what determines if we're at a leaf node? Whether or not our current node has 0 children nodes. So if node.left is none and node.right is none, then we can append to our sums list the new running sum. And here we're going to return because we're going to do a few other things below here. So if we're not at a leaf node, then we want to keep calculating branch sums. We want to keep going down in our tree. So we're going to just recursively call the function, calculate branch sums, node.left, new running sum, sums, and the same exact thing with node.right, new running sum, sums. So very easily, you can see here, this is the beauty of the recursive algorithm. We can just recursively call the same function on the 2 children nodes, the left one and the right one, and we just pass the new running sum, which has now added our current node's value to these recursive calls, as well as the sums list. Now, here you might be realizing that we're actually not handling a certain edge case where we might be at a node that has 1 child, but not 2 children nodes. So maybe node.left is an actual node, but node.right is just the none value or the null value. And in that case, we don't want to be calling node.value on none. So we're just going to add one check at the top here that says if node is none, return. And that's it. That's our algorithm. Very simple. And as we discussed in the conceptual overview of the algorithm, this is going to run in O of n time because, again, you can clearly see that we're going to be traversing through all of the n nodes, but at every node, we're doing constant time operations. These are all constant time operations. And as far as space complexity, it's also going to be O of n space because putting aside the function calls on the call stack from the recursion of the algorithm, we are returning a list of branch sums that has the length as the number of branches in the binary tree, which is the number of leaf nodes in the binary tree. There are roughly half of n leaf nodes in the binary tree, and half of n is equal to O of n as far as space-time complexity analysis is concerned. So O of n space. That's it for this question. I hope that it was informative, and I'll see you in the next one.